To achieve this, Abayomi employs cutting-edge techniques such as cryogenic electron microscopy, CryoEM, and in situ cryogenic electron tomography. Furthermore, he is dedicated to the development of potential therapeutic compounds for these debilitating conditions, employing both computational and experimental approaches. Abayomi is fortunate to be under the guidance of Professor Wen Jian, the director of the CryoEM facility at Purdue University, USA, where he collaborates with other curious minds in the pursuit of scientific discoveries. Beyond his research, he plays a pivotal role as the co-chair for biological sciences in the Microscopy Society of America, MSA, Students Council, and student project manager for the CryoVR project at Purdue University for the United States National Centers for CryoEM and CryoET. He is also the CEO of the renowned Jarvis Computational Biology Center in Nigeria. His name is Abayomi Adegboyega, and he's poised to make significant contributions to the field of biological sciences. So please join me as I welcome Mr. Emmanuel to the stage. The stage is all yours. Thank you.
Thank you. Sorry, I was muted. Okay. So I want to be sure you can hear me from online audience. And we are trying to make sure the on-site audience also can hear before we progress. And I would like to also share my screen as well. So what we'll be looking at today is majorly on the CryoEM image processing and the data analysis. I'll give a brief presentation on this. Please, before I continue, can you hear me this way? Okay, thank you. The online audience, please, if you can hear me clearly also, can you just give a comment, probably in the chat box, or unmute yourself to say something?
Yeah, we can hear you clearly. Thank you so much.
Okay, yeah. All right, so we start right now for the CryoEM image processing. Yes, today we have Professor telling us about CryoEM, introduction to CryoEM, especially, and also more about the applications of CryoEM were discussed in the evening session as well as the morning session. So how do we process the images that are obtained from the CryoEM analysis, and how do we analyze the data? So that's one of the things I'll be majoring on this afternoon. And I would like to also say, for those of us participating in this session, that you don't necessarily need to have your own sample before you can start processing your processing data. Okay, so there are data sets online Sorry. Thank you. So you don't have to necessarily have your own data set before you can process data. So you can obtain a lot of data sets freely deposited online on the EMDB. I can quickly show you how to get that. So you can type EMDB or you can type Empire, right? So European Bioinformatics Institute. You cannot see my screen. What? Please, can you see my screen? Oh,
Yes, we can see.
Yes, we can see you. We can see the screen.
ICT. Sorry, we are trying to make sure that the on-site audience can see my screen on their screen as well as those online are seeing it right now. Okay, move this thing. Okay, thank you very much. Sorry for the technical difficulty. So can the online audience see my screen? Okay, everyone can see my
Yes.
screen now. Okay, online audience, please, if you can see my screen, kindly make a comment.
Yes, we can see your
Yes,
screen.
we can see your screen.
Okay, thank you very much. Thank you. Okay, yeah. The on-site can see also. Okay. Okay. All right. So once you come to this EMDB, you can get the data sets for any of the maybe a sample that you want to use. Then I'll also show you how to use some tutorial data sets from the software that we're going to be using. Okay, so EMDB, or you can go to Empire. You can access Empire also. Just come here. Sorry. Empire. Empire database. That's the European Bioinformatics Institute, this one. So here you can easily access data sets. Once it's fully loaded, you can have it here. Okay, so these are can see CryoEM, microscope of so. So if you need any data set, you can come here and download the data set that you need. Okay, so the point I'm firstly making is that you don't need to have your sample before you learn how to process your data sets. So it's good to master the technique of processing data set even when you don't have a sample ready. So that by the time you have your own sample, we have been talking about the CryoEM stuff. And in Nigeria currently, we are using the virtual reality to learn the technique of how to do the CryoEM in real time. So many of us may not currently at this location have access to the facility to use. But if you know how to process your data set, by the time you probably travel to countries where you have the equipment, or by the time the equipment eventually come to Nigeria, you already know how to process your data set. So you just collect your samples and you don't need to be waiting to learn how to process the data set again. You know how to do it, then just continue. So it's good to practice how to process your data set, even when you know that you don't have your own personal data set ready. In fact, when I got to Professor Wenjiang's lab at Purdue University, part of the training is to learn how to process data sets using tutorial data sets and some of the data sets that have been obtained in the laboratory, in our lab, before you start your own personal experiment. You don't want to use your own personal work as a trial. You want to have works that have been done that you know this is a controlled sample, okay? This is a control sample, you know that this sample is well resolved, there are no technical issues. Then once you're able to resolve it to maybe near atomic structure, for instance, if the work that you are trying to mimic was able to resolve their structure to 2.5 Armstrong, and you are in 7 Armstrong, you know that you're not yet good enough, right? So you keep trying. So if you're able to get what they got, or even better than what they publish, then you can say to yourself, yes, I know how to process data sets at this moment. So that was one of the training I went through, and I've done a lot of data sets as training data sets before I start my own personal work. Started my own personal work. So you can come here, get data sets that you want to process. You can, if you know the Empire ID, just like you see Empire 0670, this is a tomography data set, but for now we are looking at CryoEM data set. So let's say, for instance, I know this data set is a CryoEM data set 10025. This is what we are going to be using. This is a T20S triposome at 2.8 Armstrong resolution. So you can download this data set and use it to process your own this thing. So there are many of the data set that you can always try. There's another one. So this VIP-A, VIP-B, so you can, this is a bacteria data set that you can always try. These are small data set that you can easily try at your convenience. So these are to obtain data sets so that you can start practicing before you have hands-on experience on your own personal sample for the work. So, however, I won't be dwelling much on this right now as I move to the presentation. So, oh, okay. I wish I can have this in a presentation mode, not this way. Okay, so here, I just want to introduce to you a little more to refresh your mind on some of the things that have been said, how to collect data
panoramic view of the grid known as an atlas. The atlas is generated by recording a series of low magnification images in which the microscope stage is moved systematically to maximize the coverage of the grid. The images are then stitched together to generate a composite image, and the resulting atlas is used to navigate the grid. As with grid screening, promising squares are identified on the atlas and evaluated at higher magnifications. Areas with thick ice that are impenetrable to the electron beam are avoided, while grid squares with rounded edges may indicate the presence of thin, vitreous ice. Images are recorded at the square level to...
So before this continues, so what is being done here is you've applied your sample on the grid, right? So you are about to image it. It's just telling us a general workflow. You remember we've tried VitroBot on the VR, right? The VitroBot is to freeze your sample on your grid. Okay, so you have your grid. We did glow discharge also using the virtual reality. What that is meant for is to discharge your grid, apply negative charge on it. We said yesterday that your protein has positive amino acid, then they can bind to it, stay on the grid, okay? Then now you don't want the protein to be moving, right? And you don't want the protein to be denatured. You know, you are just using the properties of protein. Proteins are dynamic. They can be denatured at high temperature, right? So you want them to remain in their native environment. So, and remain static on the grid. So what we do is you put it on that grid and you plunge freeze it using the robot, the VitroBot, or you use the GP2 Leica to freeze it in at a high temperature. I mean, that's low temperature, right? So that's about minus 180 degrees Celsius in liquid ethane surrounded by liquid nitrogen. Okay, so once you freeze that, the sample remain on the grid. Then you try to look for where there's no ice contamination. All right, you know, at minus 80 degrees, you expect that you can see some ice crystals. So, but here, you don't want any ice crystal on your sample. You just want to be able to image your sample. What you are seeing the other time, all these black dots, they are ice contamination. So you don't want that. So this has to do with sample handling. If you handle your sample very well, you don't want ice to form on it. You just want the vitreous ice, not any other type of ice. You know, there are different type of ice that you can form. So you just want the vitreous ice and you use this for this particular work.
Visualize the quality of the holes. Holes of interest are identified at an intermediate magnification and queued for data collection. After the holes are selected, the process of data collection begins by iterating through the modes of targeting, focusing, and recording. Exposure targeting is accomplished by centering the beam over each hole, either by moving the stage mechanically or by shifting the beam by a predetermined distance. After the hole is targeted, the microscope switches to high magnification to focus the image. Focusing images in CryoEM is performed away from the area of interest in order to protect the specimens from radiation damage. The focusing typically takes place on a nearby spot on the support film and
So what is happening here is you are trying to image your sample. And what you use here is the electron beam, right? So you don't want to bring the electron beam directly on the sample because it can just nature of protein, it can damage your protein, right? So you want to make sure that you have the right dose of the electrons and you want to make sure that they are focused. You have a correct shape of electron beam coming on your sample. So the technique is that you focus it on a nearby grid where you don't have your sample. So once it's focused and you have the right beam, everything, the defocus, everything is okay, then you now move it on your sample and image it. And you will know that the longer the beam stays on your sample, what can happen to it? What can happen to your sample? It will be what? Denatured, right? So that means you don't keep your beam there forever and you just go and sleep, right? So you have your timing to do all those things and image and get good quality sample. When we begin to talk about data processing, you will see how this thing comes in, how much of dose of beam that you have on it, how it affects the sample. And this beam electron also, once it comes on your sample, it can cause the protein to vibrate. Okay, so proteins are dynamic in nature. So it can cause them to move. That's what we call motion. Then when you begin to talk about motion correction in this data processing section, so that's the movements that occur when the protein is exposed to your electron beam. You want to correct for those movements, right? So you do what we call motion correction. So we'll get to that when we begin to start our data processing stuff.
Predetermined amount of mild defocus is applied to generate phase contrast. After the desired focus has been set, the targeted hole is exposed with a predetermined electron dose. CryoEM data are typically recorded in the form of short movies, and individual frames of the movies are aligned and then summed into a CryoEM micrograph. The data collection session proceeds by repeating the process of hole targeting, focusing, and movie recording across the selected holes.
Okay. So that's the general overview of the workflow of how to get your data from your sample, right? You will take images of the sample, okay? Taking images. The images you've taken, they are in 2D form, right? They are just on one plane. Are we together? Just like pictures, right? They're just on one page. But you know that your protein is not just flat. Your protein has different parts. So you take images of the protein at different orientation. So the data processing is now to reconstruct from the images that you have gotten, which are the 2D images, to a 3D model of your protein. For instance, if your protein is like this, so you've taken pictures here, taken pictures, different parts of this. You've taken pictures from this side, right? You've taken pictures from this side. So for instance, you take thousands of pictures. That's why you see that you have live data sets, thousands of pictures. Then the software algorithm has been designed in such a way that you can reconstruct that protein into the way it was before you took the pictures. Are we together? So that's what the data processing is about. You are trying to project the 3D image of your sample from the 2D image that you have gotten by taking the pictures of the protein. Are we together? Okay. So I will also go through the process just briefly. I'm trying to connect us to the lectures that we had yesterday to know where we are and where we are going from here. Okay. So here is just also a way to do data processing, data collection. Has anyone seen this in the VR? Please, you have seen it. Let me see. Okay, 1, 2, 3. Okay, good. So this is auto grid loading. Some of us have tried it. So when you put your grid on, your sample on the grid, you want to load it into the microscope. Are we together? So that's why you come to this place. You do this for to load your grid. Then you can take it into the microscope for imaging. Okay, so let's see this briefly.
CryoEM specimens are prepared for insertion into the microscope by a trained professional. Multiple grids are transferred into the autoloader cassette, and the cassette is loaded into the pre-chilled nanocab capsule. The microscope operator docks the nanocab into the Titan Krios loading station. The cassette is retrieved into the microscope autoloader, and the emptied nanocab is removed from the instrument. The contents of the autoloader are inventoried in the microscope software. This process is important to keep track of the grids that are in the microscope and to select the specific grid that should be loaded onto the TEM stage. A grid is selected from the autoloader cassette and transferred onto the microscope stage. CryoEM sessions usually begin by performing microscope alignments on a cross-grading grid. After the grid is loaded onto the stage and verifying that the instrument vacuum and temperature are stabilized, the column valves are opened and the beam is centered over an imaging area. A standard set of direct alignments is performed by a trained microscope expert to ensure that the electron beam is behaving properly and that high-resolution information can be recorded. After the microscope has been aligned, the calibration grid is exchanged for a CryoEM grid. The grid is evaluated at various magnifications to confirm ice and particle quality. Multiple grids may be screened in a single session, and the most promising sample is used for high-resolution data collection.
So this is how your protein will look like. Are we seeing this image? Am I? Okay, let me use a pointer. Okay, so you have your protein now. You've taken the images. Okay, so this is what you want to process. So I'm sure a lot of us have been doing molecular docking and all those kind of things, right? You have taken protein structure from PDB. This is how they get those structure. All those structure that you are taking from PDB and others, this is how they obtain the structure. So that's what we are going into now. How do we obtain those structures to use for the protein, what do you call it? Ligand docking, virtual screening, and the likes. So this looks very insignificant, but you have a lot of information here. You have your protein here, you have the structure here, you have the amino acids inside this, then you can be able to analyze this when you're able to reconstruct the protein from this image. So moving on to the next thing. So this is a general workflow, just a general simple workflow of how to process your data. Please, if you have any question at any point, feel free to stop me and ask your questions, okay? So you have your movies. Those pictures that you have taken, you take them in form of movies, right? Then you average them into a micrograph. Then you do what we call motion correction. I just mentioned what motion correction was the other time, and those weighting. Then you do CTF estimation. I will explain what these things are. Then you do particle extraction, selection and extraction. Remember we saw the picture, right? All those dot, small things, the proteins in the, on the grid, on the micrograph. We've seen all the proteins. So you want to be able to select your protein from there. You don't want to select ice contamination. You don't want to select impurity. You want to select your protein and extract it out. Are you getting it? You extract your protein out of that. Then you do what we call 2D classification. You classify them based on the structures that you obtain. Then you also reconstruct them using 3D reconstruction, and you refine them. And after you have refined them, you have your structure. Then you do what we call map validation. You want to validate it if what you have gotten is correct. Then you now build an atomic model, right? So what we see on PDB is the final product. That's the atomic model of the protein. Are we together? So this is how they got to that stage. And that's what we're coming into now. So just briefly mention what motion correction will look like and just show you a little bit. So motion correction and those weighting is just to correct movement of particles, right? That occur when you expose your specimen to electron beam. So you notice that the frame contains the original information and relative to low radiation damage. I explained this the other time that the longer you expose your sample to electron beam, the more they get damaged, right? So you know that they won't just spoil at once. the high resolution information will start spoiling. For instance, if you shine, okay, looking at my hair now, if you shine electron beam at it, it won't just consume everything at once, right? The tiny, tiny hair on top, they're the ones that will firstly be degrading. Are you following what I'm saying? Right? Even if you use, if you light light matches and it's burning, and you want to burn, let's say air, right? You want to burn a woman hair. It won't just burn the big parts at once, right? It will start with the fine, fine part, the small, small parts. And once those parts are getting burned, then it can now start burning the bigger part. So the same thing with the electron beam. It will start damaging the fine parts of the protein, the high resolution, the tiny, tiny part. And once those ones are destroyed, you just be left with a blob. So you don't have much information. So that's when you expose your sample to a long information. The other thing is that you have high contrast image at the later part. The beginning part, you have limited contrast for your images, but you have it high. At the later part, you have high contrast. So what do we do? The latter part is not totally, it's not as if they are totally useless, while the beginning part are the useful parts. The beginning part, even though the fine informations are retained, the contrasts of the image are not very good. So you have to now, how do I average it? From this one has a good quality. This one has a good quality. This one has bad quality. This one has bad quality. Let's merge them together so that all of them can have one simple, same kind of quality, right? So that's what you sum up so this is what you get here. You have stacks of movie frames, then early stage, which is good with high information. Then this is good with, the latter part is good with, what do you call it? The high contrast. Then you begin to merge them together and you have a single kind of micrographs that contain both good contrast and also high resolution image. Okay. Please, our participants online, if you have any question at any point also, please drop it at the chat box. Anchor, we also let me know, and you can also raise your hand if you have any question. So the next thing you do after you have done the motion correction and you have done weights, you have weighted your dose, that's the electron beam dose, you do what we call CTF estimation. This is just to correct for aberrations. You use your electron beam at a particular defocus, there's an astigmatism, the kind of shape and all those kind of things. So the overall reason why you do CTF estimation is just to improve the quality of the images that you have. All right, you are improving the quality of the images that you have. So after you have a good image or good images, then the next thing to do is to select your particles on your image. So this is a particular micrograph now. You can see some tiny, tiny proteins, right, on the micrograph. Are we together? So you want to select them. Here is another type of protein, another type of micrograph. You can see this line. These are protein filaments. You can see it. How do you get them out of the micrograph? That's what the protein, the selection is about, and also what the extraction is about. So there are different means of getting these proteins out of your micrograph. The first thing is you can do it manually. You can decide to be picking all your protein one by one with hand. And if you have 10,000 micrographs and you have to go through one of them, maybe you are picking like 50-50, 50-50 protein on one micrograph and you have 10,000 micrographs. That's 50,000, right? You know how long it will take you to do that. That was how this field started. People use manual picking. You use hand to pick. Even up to now, we still do manual picking. I still do manual picking. If you have samples that are not good enough, that the AI, the algorithm that have been developed to do auto picking cannot pick, you have to do manual picking. You pick, we call them particles, picking particles. You have to pick the particles. If you have 6,000 particles, 6,000 micrographs, you go through them one by one and pick them with hand, and it can be laborious. I did one before coming home, and it took me weeks of continuous picking of particles. And you can understand the feeling when you're picking your eyes and your hand, it can be very tiring. So the field has developed also and moved on to fully automated. You don't need to do anything. You just need to tell the program, this is the shape of, this is the size of diameter of my protein. This is shape. Pick anything that has this kind of size. And it will just go and that's what we call auto picking. It will just pick it, block picking. It just pick anything that looks like what you have said. And when you bring it out, probably it picks like 1 million particles. Then you classify them and now say, okay, you can, when you classify them, you can tell the junks that it has picked from the good particles that you have, your protein. So you remove the junks and focus on your protein. So you don't need to do anything, the program does it for you. However, sometimes the fully automated can pick nonsense, you understand? So because it's seeing different shapes and just pick anything that it likes. So the other method, which I personally love using, is a semi-automated. You go through few micrographs, you know how your protein looks like, you pick them first, and you tell the protein that you tell the program, anything that looks like what I've picked, go and pick it for me. Are we together? That's semi-automated, which is really, I think for me, I love using that. Then the program can pick for you what you have selected. So there are different programs that can be used. We use Topaz. That's one program that you use for picking, auto picking, or template picking. So the one that is semi-automated is what we call template picking. You have a template, right? You have selected a template and you say, go and pick something that looks like this. Then the one that is fully automated is blob picking. Blob, right? Just pick them. Then if it's a filament, right? If it's a filament, we know proteins that are filamentous in shape, right? Things like amyloid, things like collagens and all those kind of long proteins. So you can also use what we call filament tracer. It will help you trace the filament. You know, sometimes they may not be straight on the micrograph, it may be bent, just like this one. So the filament tracer can help you trace it and know that this is your protein. And here you can trace it. What we are doing currently in our lab, one of my colleagues called Chauchi is currently developing a program that my lab is fully wet lab and also fully dry lab. There are guys in our lab that are only working on computational stuff, developing programs for CryoEM techniques, running programs and the likes. We'll be telling you more about it also. And there are some that are fully wet lab guys. They don't do anything computational. They're just working on samples from, we have collaboration with Indiana University also, which is an hospital in Indiana University Hospital, IU. So we collect samples from them, brain samples from them, and we work on them. Alzheimer's disease, neurodegenerative diseases related stuff. So there are people in the lab that are working on that aspect, and there are some that are combining the two. You are doing dry lab and you're also doing wet lab. So, so here, the reason why I'm saying that story is because this curve filament needs to be straightened, right? So he is working on the program, developing a program that can be used to straighten the filaments so that you can resolve your structure easily from there. So that's selection of particles, right? How do you now extract it? So for instance, all these ones here are amyloid proteins. I mean, they are filaments. Let me call them filament. For instance, you have this filament. Say this filament is 150 Armstrong, the diameter. How do you extract it? So the principle is that you create an extraction box that is your particle size plus 150 angstrom. So a quick mathematics, shall I point or just ask generally? So if you have a particle that is 200 angstrom, what would be your extraction box size? Sir? No, he's a mathematician. You don't need to ask. Thank you very much, sir. So 350, are we together? So you just create a bigger box so that your particle will be inside that box that you have selected. Are we together? So you just have it out. So that's how to extract your particles. Then we do 2D classification. So 2D classification is just telling you that put all the similar particles in one cluster in the same class, right? You have thousands of particles, sometimes millions of particles. You are telling it, put all the ones that look alike in the same one, the ones that are well resolved in the same place, the junks, put them in the same place. So from here now, you can see that this is a good particle. This one also, this one also. This is just nonsense, right? This is not a good image. These are not good particles. These are not good particles. So you classify them and make sure the good ones are in the same class. The poor ones are in the same class. Then you discard the poor classes as junk. Then you go ahead with the good classes. You can see this is a good class now. Then you go ahead with this to continue your structural resolution. So you have the 2D classes. You can't get good enough information from here. You need to reconstruct them to a model of your protein, the 3D model. So you come to what we call 3D reconstruction and refinement, right? So what you do here is you can have an initial model or initial reference, as the case may be. So this initial reference can be a previously determined structure. If you are working on the structure of insulin, for instance, you have insulin structure already deposited on the PDB, right? So you can download the map, the CryoEM map of insulin, and use it as a starting point for your own sample as a template, right? So, or reference, as the case may be. So you use that, and it will make your reconstruction to be fast. You are giving it an example that, okay, this is how my sample look like, even though I may be getting a more detailed information from my own sample that these people did not have, but we are working on the same sample. So it will firstly reconstruct your image to look like that, then you can continue refining to get a better structure from what you have gotten. Okay, so it can be an ab initio reconstruction. What that means is you are de novo. Ab initio is also like de novo, starting from scratch, right? So the program generates the initial model from your sample data, right? So it will just give you, we are going to run this practical. I will run you through the software to see how these things work. So, or it can also be the result of the previous iteration and the likes. So after you have reconstructed the 3D image, then you refine them. Refinement is just you continue to refine it until it converges to a good resolution, and you are seeing fine details of your protein. Are we together? Fine details of your protein. If it's having a curve, you are seeing it clearly and all those kind of things. So once you are done with the refinement, then you can go to the validation of your map and also now begin to build atomic model. So this is how your map will look like. What is inside here is your protein. You are building the backbone of your protein into the map. Are we together? So this is how we get to have PDB structures. So you're now building your, if the shape of your map looks like this, looks like this for online audience, you want to see what amino acid looks like this. Are we together? What amino acid looks like this? So definitely, you know, it cannot be glycine. It's just maybe small, this thing. You'll find maybe a bigger amino acid that has aromatic ring and has a side chain. So you fit it into that map to see if it's fitting. If it doesn't fit well, you try something else. Maybe you can try tryptophan, try phenylalanine, try those that look alike and see if they fit. If they fit well, good, then you move again to the next part of the map to see how does it look like. Then you fit another amino acid into it to see if it's working. So usually you can start from the de novo to fit all your amino acid into the map, but it will be very strenuous. So there are software that will just firstly help you get a backbone, then you can now begin to adjust it. So the next lecture, which is will be presented by Professor Kiara. If you know anything about informatics and structural biology or computational biology, probably you will have heard about Professor Kiara. He's a very well-known professor outside the United States or United States. We are very privileged to have him to give a talk. They develop a lot of programs that are used widely worldwide to do CryoEM structure resolving, things like there are programs that looks like AlphaFold. If you have any knowledge about what AlphaFold is, they develop those kind of programs. So they have a lot of programs that they use. We also use them. You'll be talking about how to use programs to just predict that, and some of the students will be coming also to tell us how to do it. They'll be presenting the software that we use and the software that the lab has been using. And they won't go into technicalities of how those softwares are being developed. No, we are users at this time. So they'll be showing you how to use those programs. Okay, so there are different programs that can be used. More than protein, they develop programs for RNA, DNA, and all those kind of things. So they'll be coming on board the next session to show us how those programs are being used. So this is his lab. This is just a suite for CryoEM alone. See different kind of programs all these are programs that are being developed for CryoEM alone. So if you can go to his website and see their tutorials, video lectures on it. They do a lot of neural network, deep learning, artificial intelligence kind of things to do that. So we are fortunate to have him at Purdue and also in the structural biology department in our building. So I was very privileged to be able to walk to his office and share the idea with him that this is what we are doing in Nigeria. And very nice professor was willing to come and give us a talk and also to expose us to what is happening in the developed world. So we will move quickly to a case study. This is still a presentation case study on ABRI data sets. This is one of the data sets I worked on also using Relion. ABRI is just like a peptide, 34 residue peptide that is the major component of amyloid deposit in familial British dementia. One of the things we do in our lab is neurodegenerative diseases related structures. Work on samples on dementia, samples on Parkinson, tau protein, prion protein, and those kind of proteins. Samples related to Alzheimer's disease. So this is one related to familial British dementia. So we work on this sample. It's for my training. So this Relion. This is how to do use on Relion. I won't be using the practicality of Relion right now, but I'll be using the second software, which is CryoSpark, which is faster and more user-friendly. Relion is a very wonderful software, but it has some technicalities that you may need to learn better to know how to use. So you import it. I won't go into the detail right now, just to show you a brief overview. This is motion correction. Just like I said the other time, you have your protein moving, right? These are different proteins. So they move from one point to the other during the collection of the data. Then you correct for that motion that you have seen. That's motion correction. So you have your CTF estimation, you see the turn rings and the likes. Then you pick the particles. These are particles that you're picking. These are ABRI particles. You just pick the sample. Okay, you extract the particle and do some 2D classification. So here are 2D classifications. Can anybody tell me which of these is poor? Which of these 2D classification is poor? At least from the simple lecture that we've gotten just now. This is how your sample look like, right? Your image on the micrograph. They are long, long threads. And we've classified them into this. From physical participants, online participants. If you want to say something, please just let me know. Then we can accommodate you. Which of these will be poor? Which of these 2D classes will be poor? Is poor.
Hello?
Oh, okay, please go ahead. Yes, we can
I
hear
think
you.
the one with 3.50236E04.
Oh, fantastic. Please, can we clap for him if it's possible? Yeah, thank you very much. Thank you very much. Because this is just like a junk particle. This is just like a junk particle. You are not doing anything wrong if you don't know right now the one that is poor. It took me a lot of time before I can, those days, you just be seeing the micrographs and seeing threads and see everything. You don't even know which one is good, which one is bad, which one, you won't understand until someone pointed to you that this is this. So and that's what we are doing. That's the reason why we are here. Okay. So this one looks poor. So you can select some of and you can see that these are different types of filaments right now. So you classify them and resolve their structure as the case may be. So you see, we did particle extraction. This is manual picking, right? Using hand to pick. I told you that time that what I love to do is to firstly pick some, use it as a template for the next one for the auto pick to do for me. So this is now Topaz. We have trained Topaz. Topaz is a software, it's just like an algorithm that we have trained to run auto pick. So these ones are picked by the computers, by the computer, all the other ones. Okay. So you can see that you have more particles and more well-refined structure. Okay. So after this, we want to build initial model. There's a software called HLSQ developed by my professor, Professor Wen Jiang, and the lab mates. The lab students also. So this HLSQ is a software that you can use to generate initial model, right? Can we remember what initial model or initial reference is? We talked about it just now. Can anybody remember? On-site, online? Yeah, I saw the answer of Musbahu Ahmed for the last question. You got it right. Thank you very much. Okay, for this question, who can help us? Initial model, initial reference for 3D reconstruction. Can anybody quickly pick it up? Is anybody willing to answer the question? I want to be sure you are following what I'm saying. Yes, thank you very much. That's just it. Thank you, ma. Please, can we clap for her also? Let's appreciate her. Yeah, it's just like a template. Initial, right? Then reference. This is my template for you to use to reconstruct the bigger one. Are we together? So that is what it is. Thank you, ma'am. We wouldn't have left this stage if we cannot get that question. Okay. So the HLSQ is a software that you can use to generate initial model. Okay. So, and this lab also, generate a lot of, we build a lot of computer programs that you can use, starting from sample preparation to data collection, to image analysis, to 3D reconstruction, to structure analysis, for training and the likes. So, and they are free software for academic use. So you can visit the GIANX lab, just type the GIANX lab, Purdue University, you will get softwares that you can use for training. And for those who are interested in protein ligand docking, you can also find the software there that can help you quantify for protein ligand docking, the concentration and the likes of what to do. They are all there. So you have the 3D classification. I won't go too much into all this anymore. Then I won't go too much into what FSC curve is and the likes right now. Then you get a final density map and you use it for the atomic model building. Okay, so inside here now, this is just my own practice data set. You can't say it's the best in the world, but at least we're able to get 3.3 Armstrong resolution using using Relion at this stage for this. And I did this work some months ago. So of course, I think I'm better now at it. I can get a better structure than this. But you can still see that you can have the backbone of your protein, right? This is a protein structure that looks like S. So you have the backbone. So if you look at this properly, you can be able to trace what kind of amino acid backbone looks like this. Then you can begin to fit your your model into this, your atomic model into this. All right, so I will end the slide presentation at this point to accommodate questions. Please, Anchor, let me know if I still have time and when my time is about ending. Okay, so please, if you have any question before I move to the next practical section, which is more on the use of the software, please let us know before we move to the next thing. I still have 1 hour more for the practical session. Okay, thank you. So let me see how we can manage the time for this. So the CryoEM software has been installed here, and you can use your web browser to do it. So here, I'm connecting right now to one of our workstation at Purdue. You can see the address. If you try to connect to it, it may not work because you need access to it. So, but you can install the CryoEM by yourself on a Linux machine, right? So how to install it, I've sent the link out, or some of our facilities have sent the link out to the WhatsApp platform and also to your emails on how to install, how to download CryoEM and how to install it. So, but it works, the installation works on a on a Linux machine. Then once you have a Linux host, then you can connect to it using any other type of computer. So I'm connecting with it now using this Mac, but the host is on a Linux somewhere in the United States. Okay, so and instead of starting from the scratch, just yesterday, I just quickly ran this overnight to have a structure that we can use to explain what the whole stuff is about. This is just like a simple general workflow of how to process data, and you can do this yourself right now. You don't need to wait till you have access to facility before you do this. Just try to install the software and start practicing. Okay, so so this is a simple data set that you also, if you go to CryoSpark tutorial, you can also get the same data set. Remember, I've explained Empire, how to get to Empire and download your data from there, just briefly. So Empire 10025 contains T20S triposome data set. So, and you have 196 micrographs there. But what I've used to process this, because I want to be very fast, is just 20 micrographs out of 126. I mean, 20, you see 20 movies here. And from the 20 movies, I was able to get 2.91 Armstrong resolution. This is near atomic resolution, right? So, and this is good enough for a start. So, so what I would do right now, okay, I think I should just create a project from scratch. Let me show how to create a project. Okay, so if you have access, when you have access to your CryoSpark, you will have this home page looking like this. It should load. Okay, it should look like this. Some of the things you have done in the past and the likes. Then you have new projects. If you come here, you have new workspace, new session and the likes. But we want to start, let's say we are starting new project. New project, you want to have a tutorial, you want to have a name for it. Let's call it T20S proteasome. So here it's asking you what directory do you want to work in. So let's access our directory. So you remember I said that I'm connected to a host. So I'm accessing the host directory right now. So I'm taking it to CryoSpark projects. And I'm taking it to my own account. And I want to work here. So let's just put it here. Okay, so let's create that it's coming to that place. Then what should be the title? Let's just say T20S. And we're creating the workspace now. So we have this particular workspace created. So you can start from any part here. If you have, okay, question? Yeah, please. Yeah. Yes. No. No. The reason why I depended on a host right now is because I cannot run it on this particular computer. Yes, I can't run it on this computer. You need to run it on a Linux machine. So that's when it's fully installed. Yes. Yeah, thank you. So, so you can start from movie, you can start from micrographs, you can start from particle or different kind of things. Okay, thank you for the, I'm seeing some comment in the chat box. Thanks for the comments. Thank you very much. All right, so here now we can start from different parts. Okay, so let's say we want to import movies. If you want to import movies, you go to the movie, then you put all these parameters and you import them. But I want to do something a little bit maybe easier. So I'll come to this workflow. CryoSpark also have tutorials and tutorial data sets that you can use, right, for practice, which is very smart. So here, this is the T20S that we talk about, introductory tutorial, right? So I will click on it that I want to use this. So it will show me all the steps of what I need to do. Firstly, you import your movies, you do patch motion correction, CTF estimation, block picking, inspect the particles, extract to the classification. All what I've said the other time is showing that these are the steps that you should follow, right? The only thing is asking from you is, where are your downloaded movies? Because they are not downloaded here. You see this part is flagging two things, right? Movie part and the gain reference, right? So you need to add those two files. And those two files will be in your download. Once you download your T20S potassium, you will find them inside. So, and it has given you all the parameters included, the raw pixel size, the accelerating voltage, the spherical aberration, total exposure dose. All these are what you used when you were collecting your data on the microscope. Can we remember? So we collected the data set at the voltage of 300 keV. Then total exposure dose, your electron exposure was 53. So you need to notice all those details when collecting your data, so that when you are processing your data, you are putting them there. This is what I've done, this is what I've done, then process it based on this. So here now, let's set up the movie part. So I have this movie part also. I think it's permit me to duplicate this. One of my colleagues in the lab, I just told him quickly to help me create a subset of this data set so that we can use for this training. Okay, so instead of using all the movies, because it will take time to process, so I'll just use very small part of it, so 20. So the movies are in its directory, so I'll pick it from there. So I think I have it here. So this is the one that I ran before coming just a few minutes ago. Yeah, I want to know where they are. So it's in Jiang. Please, can we all stay muted if it's possible? So let's go to Jiang. Scratch. Okay. So just scratch. Okay, so rely on tutorial. Yeah. This is it. Empire, this subset. We are just picking the subset of it. Subset movie. So this is how you locate the file that you want to use. and they're in all of them are in MRC format, right? So instead of selecting everything one by one, you just use a command, star dot define the extension of the file, MRC. Okay, so using that, it will pick all the files in this folder. Then you just click select. So the gain reference file also, all these things, you collect it when you're collecting your data. So this is the gain reference file. Select it. Okay, so let me apply it. So right now, because we are using a template from what CryoSpark has created, it has given us all the steps that you need to go through as a template. If you are processing your own data sets, you will have to say from this step, I want to do motion correction next, I want to do CTF estimation next, I want to do block picking next, I want to inspect, I want to do this. So I will also show us how to create these individual ones by ourselves, okay? But from here, right now, just because I said we want to use a template that CryoSpark has created for tutorials. So it has given us everything from import movie to motion correction to CTF estimation, block picking. How many of us remember block picking? Block picking. Okay, what's block picking? Anybody? We remember block picking, we remember template picking, right?
Template, yeah.
Okay, we also remember what again? Filament tracer, am I right? Then we remember auto picking.
Right.
Yeah. So the block picking is what? Okay, yeah, someone on site is
Template
saying
picking, yeah.
okay. Let me take the on-site and I'll take the online comment. Please go ahead, sir. Good. Block picking. Thank you very much, sir. So when this process is just automated, fully automated, it just does block picking. Do we have any contrary opinion from the online audience or a supporting opinion? Please go ahead if you want to support the motion or if you want to contradict it.
No, he's very right. That's
Very
true.
right. Yeah, thank you. Okay, thank you very much. So that's what you have. So it's here now. Remember I said the other time that the block picking, you are giving it based on the diameter. So here now, the block picker is asking, how do you want me to pick? What's the diameter of your protein? Minimum should be 100 Armstrong, right? Then the maximum should be 200 Armstrong. So anything within that range, the block picker will pick it for you. Anything within that range, whether it's good particle or wrong particle, it will pick it for you. Then you can now inspect the peak afterwards. That's what this inspection is about. So you adjust the threshold. If he's speaking nonsense or he's speaking too much, you adjust it from there. Then after you have adjusted it, you extract. You extract. So while extracting, you have an extraction box, and I told you how to get the extraction box. The minimum should be your particle diameter plus 150 Armstrong. You can increase it more than that, but not too much. Because the bigger the box size, the more computational power it will use, right? And if your box size is even wrong, the more computational power it will use. So in our lab, my professor has developed, he has developed a tool that highlights almost all good particles, all good box sizes that you may likely need to use throughout your research. So once you go there, you can type on Google Wenjiang good particle box size. It will give it to you. You will see all the good box sizes that you can use based on computational justification. You didn't just come up with those numbers offhand. They are computational justification for all those good box sizes. So you can access them and use them. So if your particle is around, let's say, you have a particle that is around 300 Armstrong, and you're thinking, what should my good box size look? And you know that 300 plus 150 is 450. Is 450 a good box size? You are not sure, right? Because we say 450 doesn't mean that 450 as a number is a good box size. Let's quickly check it. Let me just pick from here. When Jiang particle, I can even say box size. I should be able to get, is that what it's meant? I should be able to get it from here. Yeah, you can see the Jiang's lab archive box size. So once you come here, how big should your box size be? This is the lab website. So he has generated good box sizes here. Are we together? So is 450 apart here? You see that 450 is not here. 450 is not a good box size. If you use 450, it doesn't mean that it will not work, but it will take a longer computational time before it can finish calculating what you are doing. So which one should you use here if you want to use?
The closest one, 448.
Okay, someone is speaking from online. 448, very good. You can use 448 because it's very close to 450, right? 448 is good. If you want also, you can still use 480, which is close to 450 also. But 448 will do a better job at this time because it's more precise to your box size. All right. So let's continue. So after you have gotten the extraction box size, you extract your particles. Then you classify them. You do 2D classification. We remember what 2D classification is. You are classifying the good particles in one cluster, and you are classifying the junks, the poor particles in another cluster. So once that is done, you can remove the junks and continue with the good particles. Okay. Then you select them. You select the good 2D class. Then you have your template picker. Now, from this, is there anybody that can explain to us at this stage what this template picker means? What's it doing at this time? From the presentation, anybody online, on-site? Template picking, what does it mean? What's it doing at this point? After you have done block picking, you have inspected it, you have extracted, and you have classified them into 2D. Now you are doing template picking. What's the need for template picking? Okay, please go ahead. Someone has something.
Hello?
Yeah, please go ahead, sir.
Okay, yeah, I think the template picking will help you get possibly amino acids that best fits what you have classified from where you can build your structure from.
That's a good attempt. Close to the answer, but not exactly. The stage you explained is still in front. This one is not yet there. Okay. Yeah, good attempt, good attempt. Any other attempts? On-site, template picking. From the name, templates. Can we remember? Now you remember that we have templates picking. We are using a template, the 2D template, to pick. Remember, we have auto picking. We are doing auto picking, right? We want to do auto picking. We want to say the computers will pick for us. We have 10,000 micrographs. How do we want to pick everything? We have picked few based on block picking. We've said any particle that is within this range, pick it for me. And it has picked it. We have removed the junks from the good ones. Then we now want to, from the good ones that we have, we want to use those good ones as a template to pick any other good ones that is still inside the micrographs. That's what the template picking is. Are we on the same page now? All right, thank you. I want to be sure that we get this thing. At least we should get something from it. I don't want to just pick and just finish the lecture. If we cannot finish everything, it's better than finishing everything and nobody get nothing. Okay, so please, let's keep following. All right, so we have the template picker that will also tell us, pick from the template that we have given it, okay? So then we extract it, then we do another today classification, then we do initial reconstruction, which is our initial model for homogeneous refinement. So when we do homogeneous refinement, we are already getting to the structure that we are going to be using for map validation and atomic model building. So to save time, let me go to this one that has been done briefly and show you what it looks like. So this is the movie. When you finish importing your movie, this is how it will look like. So remember that you will need to insert all these parameters. Your accelerating voltage, what voltage did you use to collect it? The aberration, maybe I should, here, let me use the tutorial that we are doing so that you can see what I'm doing. Build. Okay, so this is the first thing. You want to import your data, right? Are we together? You want to import your data now. We have put the parts the other time, we put this. Then the accelerate the raw pixel size. How were the images taken, the pictures? What are the pixel sizes? You take it, this is a super resolution pixel size. So you take it to put everything. Then you run it. Q job. The reason why you are seeing all this is because in the host lab workstations that I'm connected to, you have different types of computers there. You have the one with GPU, the one with CPU and the likes. So I'll just use default. So once you queue it, it will launch it and we start running on that computer. So you have the movies here. So once this movie finish running, it will look like this. It will look like this. These are your images that you've taken. These are micrographs that you've taken. So these are the proteins. You are seeing them in different orientation. This is one side view. These are another side view. All these are proteins. These are the proteosomes, right? So just look at them. Then after the movies, here now we have 20 micrographs, right? So after the movies has been imported, we want to do motion correction. Let's see. The reason why I ran it before is because the computers may be occupied. So it just started now. So this movie will finish, then we can go to motion correction, but I won't wait for it to run. Some of these things is because CryoSpark is very fast. That's why you can attempt to run it. Sometimes it may take you weeks before you get the structure. Yes, sometimes months. Yeah, I've been trying to resolve a structure now for more than 3 months and it's not yet done. In those days, sometimes you can use your whole PhD career to resolve a structure. So from sample collection, preparation, to processing your data set to obtaining a structure. It's not a 1 week job. That's why it's good if you practice how to process data sets before you start collecting data. Because you may have problematic data that will not give you any good resolution at the end. You finish processing for months and you are now getting maybe like 7 strongs. That's not good for anything. So you have to start again. Are we together? So it takes time to build this. So, but now it's getting faster. Right now, you can resolve a structure within 1 week. Yeah, you can resolve a structure. If you have a good sample, you've collected your sample, you have a good sample, and you start the program and you start the processing, depending on the software, the computer that you have. If you have a good computer with GPUs, then you can run them on it. You have 48 gig GPU, take you some few minutes to run some part of the job. Okay. Constantly on. Constantly on. So now you see this. Let me see if someone can get what I'm showing. What's the difference between this one and this one? This one and this one. These are the ways you detect errors, right? You can see that there are lines. This one is looking somehow. Let me open it so I can see it clearly. Yeah. It's showing you some exposure that are not supposed to be there, right? So this is telling us that this micrograph, there is an error somewhere, and we have to detect what's the error. From my own practice, I know that it's the gain reference that is giving this error. The gain reference is just like an average of the distance. So here, what is happening is just that we just have to flip the gain reference file. If it's flipped upside down, it will give you something like this. If it's flipped in a different direction. So from practice, also I had a lot of challenges understanding why this is the problem initially, but people in the lab eventually put me to that this is the problem. If you continue processing your data set like this, from the scratch, you have already made a mistake. You can't get any good results from it. So let's clear the job and rebuild it. Then you see flip gain reference and deflect file in y-axis. So this is, if you do this now and you flip, you will see that the resulting image will be different. So because of time, I won't wait for everything to keep running. So we've done this now. Then this is the motion correction, which is the next step. You do the motion correction. For motion correction, you will see graphs like this. All these are showing you the motion of your protein and how it's being corrected for. So I'll show you the input parameter here. Number of plots. So now, one good thing that we need to learn is how to connect this first job, the second job, the first job to the second job. Okay, because you won't always have them like this. I'm using a template, that's why you have them like this. So when this one finished running, I'm opening the second job now. Can we see that this is gone? That's for my aberration is gone, right? Because we have done the correct thing. So what you need to do is to, let's say this is not here. You want to start motion correction job. So you are using the output from the first job, which is your movies that you have imported, connecting it to the next job. So what we do is you carry this import movie, you carry it, are we seeing it? And you put it here. So once you carry it from there and put it here, then you can run it. So let me see if I can get 2 GPUs to run this right now. If it's available, we can run it, but if it's not available, then we'll move. Okay, it's launching. So after the motion correction is done, this is what it will look like. Then you do CTF estimation, which also CTF estimation is to improve the quality of your image. I won't go into much technicalities of how the FSC curve looked like and the likes. So once you are done, then we come to this block picking. Remember, we said block picking is just to pick your sample that is within a diameter. So you can see now that all these red dots is picking the particles that are within that diameter. So that's what you get after block picking. Then we inspect the peak. So you can see it's already rounding it. But you can see that if you can see it closely, because it's block picking, it will cut off some part of the protein. It will pick one protein and pick the other protein. It's not very accurate. And that's why it's block picking. But some will be accurately picked. So that's why we still need to do classification afterwards to get the 2D class that you can use. So you now extract the protein. So you see the extraction. The beautiful part, we're almost getting there. So after you have extracted your protein, you see a 2D class that looks like this. We're already getting to how our protein looks like. Are we together? So these are the side view of the protein. This is the protosome, right? Side view of the protosome. This is the top view of the protosome. You have this, you have all this, side view. So you will pick the good ones in this place. If I say this one is the good one for the side view, who can identify another good one that is side view, if this is a good side view? Oh, you're not seeing my pointer? I'm using mouse head.
No, we can see it.
Okay, good. Okay, thank you. Yeah. So this one is a good side view. Do we still have another good side view here? If you want to describe where it is for me, I won't mind. Please feel free, on-site, online.
Yeah, under it by your left, or counting from second one under it, just below it, then you count from second, come down, then take your right. Yeah, yes.
This one, very good.
Yes.
Very
Yes.
good. This is another good one. Very good. Wow, very good. I'm glad we are catching it. Good. Can someone identify a poor one? Side view, a poor one. Anybody?
Yes.
Okay, please go
Yeah,
ahead.
second to the last one could be. Second to the
This
last
one.
one. No, that one is one of them. If you come down again, yes, that one you're pointing at, yes.
Very good. Very good. Very good. Wow. We're already having structural biologists in the making. That's good. Please help me appreciate him, please. That's good. That's good. Thank you very much. We are making progress. So if you have your sample, you will know what is good from what is poor, right? So because the computer cannot do some things for you, you have to do it yourself. You have to use human discretion to say it, to pick it. So we have that. Then, you know, the protein is not just side view. You still have some top view. And because of preferred orientation problem, most of them will lie on their preferred orientation position, which is the side. But you still get some top view, the head. So you have this, which is top view, and they are still good ones. So you pick them. All right, so we select the good ones. This part is an interactive part that you have to select with your human discretion. So among all the 2D classes, we said these ones are the good ones. Use this for template picking. Are we understanding the dynamics now? use these things to pick the ones that are looks like this that are still in the micrographs. So once we do that, you see the template picking, we inspect it again, we do this, see the next two classes that we got. Still loading. Can you see now that we have better 2D classes than we had the other time? And the junks are classified separately now. The other times, there are more junks in the good particles. They are all mixed. But now it's been separated very well because the template picker is doing a better job than the block picking. So we have, and you can see that the top row occupies the best ones, whereas the last rows are now telling us these are the poor ones. Just classify them separately. Okay. So after that, we selected it, we build an ab initio reconstruction. Then we have an homogeneous. Let me open what ab initio reconstruction is. So this one is just using the shape of how your structure is to build an initial model, or what you call ab initio model or reconstruction. So that's that. So you see how it looks like. It's just saying, okay, this is the X, Y, and Z axis of how the protein looks like. Then you can use it to build your structure. So this is a final structure of how it looks like. I will open Chimera or Chimera X now to view this protein in Chimera so that you can begin to see how it's connecting back to what we have known before. So, okay. So now let me open Chimera to see how it looks like. So I'm opening Chimera X now. You can see the structure that we have resolved. This is a T20S triposome. So that structure, I opened it here. I downloaded it from that CryoSpark and opened it here. You can see that it's still showing you CryoSpark project also map. Are we together? So this is how we got the map. You see the top view, the side view, and everything, right? So this is the kind of map now that you will now use to build your atomic model. You validate this map if it's correctly resolved, then you now build your atomic model. You can see the side chains. All these are your amino acid side chains. Can we remember what I was talking about the other time? The hair. So these are your amino acid side chains, and this is what you now use to build the atomic model. You have to fit in the amino acids in this map. This is how to insert, this is how it looks like. And these are the parts that the next presenter, a professor from Purdue University, will be elaborating on. How do you analyze your map? You've gotten the map, how do you analyze it? How do you build an atomic model into the map? How do you fit it into it? Then talking about any other thing that are related to CryoEM map analysis and the model validation. So these notes, I will stop here and let us take questions if there are more. Oh, thank you very much.
So I think so. Yeah, so. Right. Thank you so much, Mr. Emmanuel, for that lecture. It was mind-blowing, interesting, and from the look of things, we learned so much in a very little time. So we'll be taking questions from on-site members and members online. So feel free to, indicate if you have questions. Right. Are there questions on site? All right, sir. Please, sir.
All right, now, thank you for the presentation. What I want to know is, when you were talking about that electron transfer, you're talking about the being measuring. So how would you know when it is no or not? How to know?
How to know if the electron beam is enough? Okay, there's a way on the equipment to adjust the electron beam that you are using. Most of the time, the technical director of the facility will adjust that to know the kind of dose that can damage your protein based on the kind of protein you are using. And they will test it first to see the kind of exposure that they can bring on it. Okay, and see, from many proteins have different type of exposure. It has to be tested, it has to be tried to see what quantity of dose will denature it, what quantity of dose will still be good enough to preserve it. But generally, you always image at a low dose of electron so that you don't have too much of electron on it to damage it. But you can't be setting of a particular number until you expose your electron to the protein. Okay, so, and you have to adjust it to do the beam, the focus, and all those kind of things. As you are adjusting one, the other values are being adjusted. So once you are done, once you are setting of the starting point, then you have a number. It's from there that is from the program that you extract the number. You don't give the program the number. Are we together? So you are just based on the number of what you are doing, and that's where you get the number out from. Okay.
All right.
Thank you very much for your time in this and studying the extraction of particles. There is a possibility of obtaining the good and the bad, and then both of them, we are going to take an average and give it to obtain the
Micrographs.
micrographs.
Yes.
So, if the ratio of the good to the bad, of the good to the bad is lower, presuming the bad has a higher number of particles.
Yes. To the good. Yeah, thank you very much. So that's one problem in the field. You have a problem of signal to noise ratio, call it SNR, signal to noise ratio. You have some bad quality of image. Sometimes the best way is to just go back and recollect the data. Other times you can see, try to use the programs to adjust for that if you can get a good resolution from it. But the easy way out is, if you have very poor images that you have collected, the best is to recollect the image, which is very easy to do. Yeah. Thank you for that was awesome. Good questions. Do we have more questions from the
On-site,
side?
well, for now, I've not been able to get any questions from any on-site person. Questions, please? All right, I think somebody's raising their hands. Samson.
Okay. Hello, can you hear me?
Yeah,
Yes, sir.
Mr. Samson.
Okay. So, good afternoon, everybody, and thank you so much, educator, for this enlightenment. I'm calling from UNN. I have two questions. Yes, I have two questions. The
Please, where
first
are you coming
question.
from? I have this thing you are coming from somewhere.
Okay, my first question is, we actually have a mini workspace per se, with a Linux a system we can install this. I hope to install this on. After this, it has a good CPU as well. Is there a way in which we could, have a form of guidance in case we run into issues after here on installing that? We've actually been into dockings and all that as well, basic bioinformatics and all that, and we want to step up a bit. If we could be guided in case we run into issue after now. Then secondly, it's almost obvious that we can't do the practical machine data collection and all that currently in this part of the country. I don't know about the University of Jos, but here we might have such issues here. You mentioned about databases such as EMP and the Empire database. If we're able to access a data there, I was hoping to see maybe where you will connect during the demonstration, that this is the point at which the databases or the data will collect there. This is at the point at which it is, and this is where we pick it up when we get into the Grasper workspace. If we will go into this currently here, I guess we'll have to be sorting data from already uploaded data. I wanted to know at what stage is the data that have been uploaded there is, and after getting it, what are such data supposed to contain? There were some input parameters we need to put before even building your micrograph and all that. Are such already provided in the data uploaded there, or how refined, or at what stage is those data there, and where do we continue from when we get source the data from there? Thank you so much, sir.
Okay, wow. Good questions. Thank you very much, sir. So the first one is you can reach out to us, you can reach out to the lab, to our professors if you have any question on when you are trying to install your software. Please, can we mute that for now? Okay, thank you. So if you are trying to install your program and you're having much issue, please, you can reach out. You can even reach out to the Prac developer themselves. They'll be willing to assist as well. Okay. So that's one part of it. The next question is the aspect of how to insert your data that you have downloaded from Empire into the CryoSpark software. That was the first thing we did, where it showed how you connect it. I can show you again briefly. You will notice when we're trying to import movie, that was what we're doing at this first stage of importing movie. You see that here is the host, right? I'll come to a neutral one so that you can see it more clearly. Let me clear this job and kill this job. So when you come to building, you see that I inserted this from here, from the computer. This is the movie part. This is the downloaded one on the computer, what you download from EMDB or from Empire. For now, from Empire, because I'm not working with the map, we're working with the data set. From Empire, what you download from Empire is what is here. this is a part on a computer. So when you come here, you see it taking you to a part on a computer. So this is the micrographs. These are the micrographs rather. Then you put it here. Then the gain reference file also. These two files, you always download it on the Empire dataset. I mean on the Empire database. So you get it also, you put it here. Then all these parameters will come. For instance, let me open, this data set is on Empire. Let's say Empire 10025. No, not clicking this. Should be this one, yeah. I think I clicked the wrong link in the first one. I even go to I think this. No, it's not. I'm looking for the European one. Empire database. The European, yeah. So once you get to this place, 10025, that's the data set we are processing. So once you open it up, all the data you're supposed to put in, you'll find them there. You can already see the pixel spacing. There's a raw pixel size, 0.66. Here, then there's always a paper attached to it. So if you click on the paper, all the parameters for you to run that stuff are already there. So you just need to go to the methods and materials section, data processing. Okay. Sometimes some of them will put it in a table format. Other times it may not be there. You're already seeing, once you read through, you see the pixel size and all the other information that you need. So usually you find all the information that you need on the website. Okay. So once you read closely, you just see everything. This data collection. How did they collect the data? The what's the the voltage? You can see the exposure here. This is the exposure that we're using, 53, right? You can see the resolution here. This is the resolution that we're using. You can confirm that here. Okay. This is that's the pixel size. Then you see the exposure. So everything that you need to see will be in the data collection and the data processing page. So for all the tutorial data sets, you will see them already published and you can always access them from there. Okay. Is that question properly resolved?
Yeah, yes, sir. Thank you so much. Yeah.
Thank you, sir. Okay, so if we have any other question, we can take it. I think, Uncle, do I still have to? Okay.
Hello.
Hello, please go ahead.
Yeah, I have just a small question. So I just want to know, like when you will know that I should use the CryoSpark or Reliant for the particular data set? Is it the size of protein or something?
Okay, good question. Good question. You can use either of the software from start to finish. Either of the software will do the same thing for you. The only reason why you use CryoSpark is because it's faster and more user-friendly. Okay, but Reliant will do the same thing that CryoSpark will also do for you. Okay. The same thing. Yeah, but for new users, you can start with CryoSpark. But for more advanced users, people who wants to have free control on what to do, how to program something, you use more of Reliant. Because Relion, you can write your program and also adjust some other things. But CryoSpark is easier, faster, but Relion is more complex, but we still give you the same kind of result.
So it's not related to size of protein if like this, if your protein is smaller?
No, no, it's not.
Okay.
Yeah. Thank you.
Yeah, thank you for your answer.
Thank you. Can we take last question?
Okay. Sorry, I'm asking again.
Okay.
Yeah, please. Yeah, at the end of the structure refinement and all that, we viewed one on Chimera, okay, where you were showing us even the backbone amino acids. When you were starting, you mentioned something about taking such structure for maybe molecular docking studies and all that. Is it at that particular point, because most structures we download from PDB are usually in maybe their ribbon view, yeah, and all that in their PDB format. This structure we have here, does it need extra refinement before it could be used for molecular docking studies, or idea format extension kind of changes and all that? Does it still need extra refinement before it can be used for computational studies?
Yeah, good question. Very good question. After this session, the next session that follows, we take it from where I stopped, because getting the map is not the last thing. You still need to know how to build the atomic model, how to fit in your amino acids into the map. The map is just telling you this is how your protein looks like. Then specifics of how and where the proteins are the next thing that we'll be dealing with. And that will be anchored by Professor Kiara Dasuke, with I think 2 of his other graduate students also from the United States. They'll be connecting with us and will be teaching us and showing us how to go about those kind of things as well. So that's the next stage. So it shows you are really following. That's a very good question. So after that, then the last session, after we have inserted or known how to put amino acid structure, then we now go into the batch screening, which is the molecular docking, batch screening later at night, which is the full online version that will be taken by Professor Tila Johnson. We know her very well. She has taken that lecture several times. Then we can follow and connect everything together from there. Okay.
All right.
Thank
Thank
you
you so much for your questions and your ability to give clear answers. So with that, we'll come to an end of this session. We'll be taking a break and we'll be reconvening 3 p.m. Nigerian time for the next session. Thank you so much.